Oh, there we go. Good. Okay, so I'll start by thanking all the organisers for the invitation. It is nice to get out to the other side of the world to talk to people about QMC, because the bad things about Australia are that it's too far away from everything, and nobody does QMC, or certainly not continuum electronic structure QMC, which is what I do. So, of course, I am lying. There are other bad things about Australia, and there's some of them. So if you don't go outside, the sharks and the snakes won't get you, but if you stay inside, the big spiders will get you.
How big is that in real life?
They get about that big. Yeah. But they're not that poisonous. It's the small ones that are deadly. Anyway, okay, so I work for the Commonwealth Scientific and Industrial Research Organisation, which isn't very well known outside Australia, but it's basically Australia's national lab. So they do research from all kinds of fields: agricultural, atmospheric, marine, lots of astro, because we handle part of the square kilometre array that will be in Australia. And there's about 6,000 employees. So as a fraction of the 20 million in Australia, it's actually a pretty high fraction of the population in a scientific organisation. So I work down here in Melbourne in the Material Science and Engineering division. Something that is surprising that people don't know more is that this is where Wi-Fi was invented. So they still hold the patent for Wi-Fi. Nobody knows that.
You sure about this? This is not like the internet that everybody invented.
No. We have the patent for Wi-Fi. We sued everybody successfully. Yep. Okay. So after the last talk of isospin and all complicated things that I really didn't understand, I want to bring things back down to earth and talk about very, very simple things in QMC. So basically this talk is, there's nothing earth-shatteringly new. It's basically me trying to educate myself on what these different methods are for calculating expectation values. And hopefully I've understood it and can explain it to you in a way that some of you might get something new out of. So the reason for doing it is that if you come from a DFT or quantum chemistry background, then you're used to getting all these lovely properties at the end of a calculation. So you do a Gaussian calculation, and you ask it for nothing other than the energy, and then at the end it spits out all these multipoles and hexadecapoles and all these complicated, nice things that chemists want. And they are easily accessible. So these are some of them that you can get from Gaussian, these hyperfine terms, hyperpolarizabilities. And we just can't get most of these in QMC. And most people say, "Ooh, why would I use QMC? I can't do all of these nice things that I can do with DFT, for example." So what I want to talk about is how you can calculate some of these things. And so I'm talking here about simple estimators that you can write as a simple time-independent expectation value in a given fixed state, usually the ground state. And we all know that the two problems that you face when you do this are a systematic bias and a large statistical variance, which makes it very hard to do these calculations. So I'll flip backwards and forwards, I think, between bias and variance, but we'll start with bias. So Diffusion Monte Carlo, we know that the source of the bias is basically that we use the mixed distribution, psi naught, psi t, rather than the pure distribution. So unless your wave function is an eigenstate of the operator you're sampling, you'll always get some bias that depends on the quality of the trial wave function. And there are plenty of methods around for trying to get rid of this bias, and they all have their pros and cons. So I want to restrict myself to the first 4 on this list, purely because I don't know enough about reptation or pigs to say anything sensible. But that shouldn't be too bad. They're all related at the end of the day anyway. So extrapolation is the simplest one. I'm sure everybody knows about this one. This is from whenever, 70s. So the idea is you write your exact wave function as a perturbation around a trial wave function, and then that lets you express the DMC expectation value in terms of the VMC value and some first order perturbation and then some second order terms. And it turns out that if you do this for the exact expectation value as well, then you get something that looks very similar in the first order, and you can simply cancel them out. So this gives you cancellation of the first order error, and you're just left with something second order. So it's very, very simple. Every code will do it without modification because you've already got your DMC and VMC values. But the problem is it's approximate, and it relies on having a reasonably good wave function to begin with. So If you're bloody minded about things and you want things absolutely perfectly accurate, then you have to go a bit further. And the standard fallback method in QMC is to say, well, I want the exact pure distribution. So I've got the mixed distribution, so all I need is this factor of psi naught on psi t, right? Simple. So a trap that people fell into, I think it was in the 80s, was thinking that, well, DMC transforms my wave function from psi t squared from a Langevin thing with branching into psi naught psi t. So therefore my branching weights are giving me psi naught psi t. So I can just square them. But of course you can't, because what you actually have is it's the average of the weights at a given point that give you this factor. So it's a bit harder. But there's also, I'm sure everyone knows, forward walking. So in the mid-70s, there's a nice proof that you can get the same factor by looking at the asymptotic number of descendants of a walker at a given point. And there are various more and less complicated ways of calculating the progeny of a given walker. But there's a very, very simple way of doing it as well that doesn't seem to be talked about very often. I think it's originally due to Nightingale. I've only ever found it in a book chapter. And the idea is, instead of calculating the asymptotic number of descendants and then weighting your value by it, you can do it automatically. So all you do is you say, well, let's have a vector associated with each walker, and this is my sample of my property A at step 1, at step 2, at step 3, and so on. And then as the walkers branch, this vector gets copied with the walkers. And so if I have 2 walkers here that branched at this point here, then we know that this many steps in the past, they had the same value in this element of the vector. So all I have to do is, if I'm at this step, I actually sum over the backwards stored steps, and it automatically includes the weight. So that's all very simple. And we know that forward walking is always said to have these problems. It's not usually that bad if you have a fairly decent wave function and a good algorithm for your DMC sampling. You can actually do some reasonable things with it. But of course, you have to project long enough to get completely decorrelated samples. And if you have this unfortunate situation that you have to project for too long, then you will start to get this hideous instability and your errors start to grow.
So the right-hand side is the left-hand side for longer time?
Yep, so you can't really see it. That's to 800 samples and that's to 10,000. Yep. So eventually the errors should start to grow exponentially, because all of the walkers will be descended from a very small number in them of the original walkers. So the other failing of forward walking is that you can't do differential operators. So if I have some differential operator that has to act on a state, then even if I manage to correct the distribution properly, all I'm going to get is the localized projected operator over the exact distribution. So that's still a problem. So we'll leave bias for now and jump on to the variance problem. So obviously, energies have this zero variance property, where if I have a poor wave function, I'm going to have massive fluctuations in my samples. But if I have a good wave function, then I can have very, very small fluctuations in my samples. I've never seen this talked about anywhere, that for some properties, if you have a good wave function, you can actually get a larger variance than for a bad wave function. So this is a really simple example, just helium, looking at the square of the electron nuclear distance. So you get a much better expectation value, quite close to the exact value, but the variance actually increases. And of course, the problem gets even worse because we have estimators that have infinite variance as well. So these are characterized by these massive spikes and horrible violations of all kinds of theorems. And there are actually different types of infinite variance that we can talk about. So for want of a better word, I call these types algebraic singularities. So basically, this is obviously caused by when an electron gets too close to the nucleus, you get these massive fluctuations. But there are also nodal surface. divergences as well. And they're much harder to deal with than these algebraic ones.
Have people looked at histograms of this? Is there any understanding of when you get large values or how common they are? Because the majority of the values that you get there are small.
Yeah, yeah. Well, it's when an electron's getting close to the nucleus, basically.
Right, right.
Yeah, it's literally just in that regime. And actually, understanding when that happens is key to being able to get rid of it, which I'll say something about later. So, possible ways of getting around some of these problems are to use perturbation theory. So this is work that I guess was started by Asaraf and Caffarel in the early 2000s, well, introduced into QMC by them. And the basic idea is, I have my local energy in DMC over the mixed distribution, and I know that that's equal to my energy over the pure distribution. So in this case, you can imagine psi naught to actually be a fixed node wave function, lowest energy fixed node wave function with specific nodal surface. So if I perturb the Hamiltonian by some parameter lambda, and this is the operator that I'm interested in, then of course we still have that the energy is at a given lambda is equal for both the pure and the mixed expectation values. So obviously you can differentiate the two and they should be equal. On the pure side, you can use the Hellmann-Feynman theorem. So you should have the pure expectation value of something. But when you've got the fixed node approximation, you have to be very careful, because for an approximate node, you're going to have a discontinuity in the gradient of the wave function as it gets to the node. So acting on that with a kinetic energy term gives you this delta function. It doesn't affect energies, but when you take derivatives, it actually sucks out the value of the derivative of the wave function on the nodal surface. So basically, this term here, which is essentially d lambda psi t, because you're going to have to tell it what the response to the nodal surface is basically telling it how the node responds to the perturbation. So if we want pure expectation values, we have to make sure that this is 0, basically. So this is the formal expression, and this is what we can actually calculate, just the derivative of the mixed energy, with the derivative of the local energy here, and then this term that involves the derivative of the mixed distribution. So that will look very familiar to anyone that was at Saverio's talk yesterday, because it's essentially the same thing with forces. Okay. So obviously there's a zero bias principle there from using perturbation theory, but there's also a zero variance principle as well. So in normal DMC, we have zero variance because our local energy looks like this, and we know that h psi equals e psi, so if we had the exact wave function in there, this would just be a constant, hence zero variance. This happens at every order of perturbation theory as well. This is simple to see, because all you have to do is look at the derivative of the local energy, and then consider the derivative of the Schrödinger eigenvalue equation, and these two things look identical. So you have zero variance if the wave function is exact, your trial wave function, and the derivative of the trial wave function is exact. And of course that goes to higher order as well. So at every order of perturbation theory, I have to get one more thing right. So the second derivative of the trial wave function and so on. Now, the trial wave function itself, it doesn't actually affect the expectation values if this is done exactly. So the only thing it can do, if we're assuming that this nodal response term is 0, is affect the variance. So therefore, it's some kind of extra degree of freedom that you've got to try and minimize the variance. Of course, if you're looking at nodal response properties like a force or a vibrational kind of thing, then you really do need to tell it about the nodal response, and then your first order trial wave function is a physical quantity. But if not, then it's just some nice auxiliary function. And so you can think of it, instead of being the derivative of the trial wave function, as being a trial derivative of the wave function. So it's a subtle difference, but I think it helps how you can think about this. The frozen node approximation that I'll refer to later is basically saying that we force this trial derivative of the wave function to be 0 on the nodal surface, just to make absolutely sure that we get an unbiased expectation value. And the way this is usually done is to define another quantity q, which is multiplied by the trial wave function, so that this function obviously goes to 0 explicitly on the nodal surface. So it's surprising, I think, that given the potential power of this method, it's actually not been used all that much. In fact, there's only 3 applications that I know of that this has ever been used for. The first case was forces in all electron molecules, and this is where the whole idea came from in the first place with Ashraf and Kafaral. And the basic idea here is, when you do your force, you have this derivative of the electron nucleus Coulomb term, and as an electron approaches a nucleus, this is going to diverge as 1r squared and give you this nasty infinite variance term. So all they did was define the Q that gets rid of that. So I take the Q and put it in my derivative of the local energy, and it magically cancels that term and leaves me with some other terms. And the improvement you get is absolutely spectacular. So from the large samples here, which is the bare derivative of the electron nucleus Coulomb term, you then get this flat line from this improved estimator. So it was one of the first steps towards an actual straightforward way of doing forces.
Basically, so putting this Q is an approximation, or is it exact?
No, it's exact, because Q can only affect the variance. It can't affect the expectation value. So, yeah. So you could choose a Q that made your variance worse. You just have to be clever about how you do it. The only other examples of this being used were to regularize delta functions, basically. So this is one. The second application was by Toulouse, Ashraf, and Emrigar, and they were interested in looking at the spherical average of the intracule density. So basically the electron pair separation averaged over the entire system and then spherically averaged. It's called an intracule in quantum chemistry. Although I was told that isn't the right thing to call it in Italian because it means something not nice, and I forgot until now. Okay, so basically the idea is we want to sample a delta function. And the way you would normally do this is you would bin it or you would regularize it in some way. But there's always, to get the exact value, you would always have to take a limit. So the limit of small bin size or some Gaussian width that you would take to 0. And in that limit, you would always get an infinite variance problem. For example, if you're binning, then the chances of an electron falling into that bin as I make the bin infinitely small is 0. So this is a really neat way of getting around that with absolutely no discretization error. And so Toulouse and friends used this version of Q to cancel the original delta function. And they then used it to look at the effect of electron correlation. So this kind of quantity is really nice to be able to look at very subtle effects of electron correlation in molecules. So basically this kind of plot here from their original paper is the difference between the fully correlated DMC version of this and the Hartree-Fock version. And you find that you have to be very careful on what kind of multi-determinant wave function you use in order to converge this properly. I later used this in a really simple problem on the hydrogen molecule. So if you look at the orders of magnitude here, that's about 0.3, and this is about 4 orders of magnitude lower than that. So you need estimators of this kind of quality to be able to do really, really high precision work, even in simple systems. So what this allowed us to do was to look at this regime out here. And it turns out that there's a secondary Coulomb hole that wasn't known about out here, and that's since been shown to be a general property of 2 electron systems. So what this is basically saying is that at very long distance, correlation actually brings electrons closer together, which is completely counterintuitive to this obvious bit at low distance where correlation makes electrons further apart. Okay.
What is the trial wave function you're using in this case?
In this case, in the hydrogen case, so it was very accurate. It was single 1s slaters on the nuclei, and then a Jastrow that contained electron-nucleus correlations, and then a very high order expansion in that. Okay, so the final application that's actually been used so far was something I did a couple of years ago with contact densities. So my interest in this is to be able to eventually be able to do hyperfine interactions with QMC. So the first step in being able to do that is to do the isotropic Fermi contact term. So this is basically the probability of finding an electron at the position of a point nucleus. Because it's non-relativistic, we have point nuclei and it's nice and simple. Again, it's a delta function, so we want to regularize a delta function somehow. And the simple way you do this is you start from a Laplace expression for the delta function. And then that, so the delta function is my A that I'm interested in here. And then what I want to do is choose Q so that these two terms cancel exactly. And obviously, this is a simple way of doing that. And then we're just left with some sum out here involving the gradient of the Q that I chose and this, the usual quantum velocity term. So that obviously gets rid of the first term, but you then have to be very careful when you do this about looking for possible instabilities in the thing that you're left with. So for example, if you do that, then you're still left with a slight problem. So this histogram shows samples from different ways of calculating the contact density. So the previous best way of doing it was the red line. So you can see it has this incredibly long-ranged fat tail, and in all cases the mean value is actually this grey line here. So peak a long way from the mean and incredibly long-range tails, technically infinite variance. If you do the first choice of Q that I showed you that just cancels that Laplace expression for the delta function, then we get the blue distribution. So it's better, it's very sharply peaked, but the peak is a long way from the mean, and we still have these long-range tails. The reason for it is that that gradient of Q acting when an electron gets close to a nucleus can still cause nasty divergences. So you then have to play with that and try and find some algebraic way of getting rid of that problem. And that leads you to another version of Q, which is your original value plus some other term. That gives you the green histogram. You then go one step further and try and get rid of that kind of divergence, and you eventually get left with this other term, which is the sum of my first two terms, and then this linear term. And in that limit, the action of del Q with del psi t actually becomes constant at the nucleus. So you can't do any better than that in this method. And then that gives you the black distribution. So we're peaked very close to the mean, and the tail, it's not as symmetric as you'd like it to be, obviously, but the tail falls off a lot more quickly than the other methods. So that's the general method you use for trying to do this. You look at obvious physical instabilities, and then you try and algebraically project them away. So as I said, they're the only 3 applications in the literature so far. I've gone further, kind of, not finished, but so that term, the contact term, is for the isotropic Fermi contact term. So we've also done the anisotropic contact term, which is essentially the electric field gradient at the nucleus. And that is a massively divergent quantity, but we're kind of getting some way to regularizing it this way. Okay. So, switch back to zero bias again. Remember that this is the thing we're trying to calculate. So that first term with the derivative of the local energy is what gives us our zero variance principle. And we can get rid of all these nasty fluctuations. But to get true zero bias, we still need to be able to calculate this term out here. And some people know how to do this. CSIRO knows how to do this. It's obvious in some senses, but a lot of people don't know how to do this. So if you read the force papers of Richard Needs' group with Alexander Bedinsky, they go to all kinds of lengths to try and get around the fact that they don't know how to calculate this. It's not nice when you calculate it, but it is doable. So before I show you how you can do that, really quite simply, consider a couple of approximations. If you had, so this is the hard term, obviously, the derivative of the exact wave function. If you set that to 0 and then expand all this, then it turns out you just get the normal DMC mixed estimate back, except this time with potentially a 0 variance. So that's normal DMC. If you assume, some people call this the Reynolds approximation, but I'm not sure where it comes from. So you're assuming the logarithmic derivatives of the exact wave function is the same as the trial wave function. this is what CSIRO was doing yesterday by writing the derivative of the Green's function as del squared, as del of psi t squared. It's exactly equivalent, I realized. And what this does is actually quite remarkable. So this is the intracule from the paper by Toulouse and Umrigar that I recalculated. So this is a Hartree-Fock calculation where you don't have an electron-electron cusp. So there's zero gradient at the origin, whereas you should have a finite positive gradient. The blue is what happens when you do Hartree-Fock and you add this approximate zero bias term. It gives you the cusp back even though your wave function didn't have it. So it's making up for your ignorance, basically. But if you have a particularly bad wave function, then there's only so much it can do for you. So here's the force in H2, which of course we should be able to do exactly because it's nodeless. And the thick black line down here is it's the derivative of a Morse potential fit to the DMC energies. So do the energies, fit the curve, differentiate it. The top section are the forces you get using the Asaraf and Caffarel renormalized force estimator, but in the DMC mixed limit. And then you add the approximate zero bias correction, and you get this. It's much better, but it's still very bad, because the trial wave function in this case is literally a 1s orbital on each nucleus, nothing more. Okay? So we have the next question of how exactly are we going to do this exactly? Well, we already know that DMC gives us something in the limit as tau tends to infinity that's proportional to the mixed distribution. So why don't you just differentiate everything manually and see what happens? So you do this, and obviously you get the derivative of the mixed distribution, which is what you wanted, with the same coefficients as the original distribution, so ratios are going to work nicely. But because of that term there, you also get these contaminant terms, which are proportional to the mixed distribution that you had in the first place. And in particular, you get a term that's ever increasing linearly in tau if you don't have the correct first order energy. Now, the interesting thing about this is even though you get this contamination that's constantly growing, it can't affect our expectation values. Because if you plug this sum of the first order mixed distribution and mixed distribution into the integral we're trying to do, then all you get is the expectation value of EL minus E naught over the mixed distribution, which is 0. So it can't do anything. What it can do is affect the variance. And that's a very important aspect of it. And I think one way that's nice to look at the reason that this thing appears is what you're essentially doing is, in DMC you're solving the Schrodinger equation, in first order DMC here you're solving the first order Schrodinger equation. So take the derivative of it and you get a Sternheimer equation. Now that's actually weakly singular in that I can add any multiple of the original solution to that first order term and still get a valid solution. So it's completely natural that this should appear. And this will continue to appear at all orders of perturbation, but they will always cancel out in some clever kind of way. Right. So how do you do this in practice? So if we take our normal DMC evolution equation, then we have our distribution after m time steps is just a product of our short time approximation to the Green's function over a whole bunch of steps. So if you take the derivative of it, it's nice and easy to write it in terms of a sum of the logarithmic derivatives of each individual time step. So all you do is you use that as a weight, and that's it, basically. You can write it as a weighted sum. Now, practical application, if you're doing a simple Green's function, then you're going to have a term from the drift diffusion Green's function and also some contribution from the branching Green's function. So the drift diffusion term has this contribution from the gradient. It's actually the derivative of del psi t on psi t, but it's equivalent to the gradient of your value q that you've got. This isn't noise controlled. I don't know of any zero variance principle or anything clever going on with this term, so this can cause you problems. The branching term, on the other hand, is really nice because it involves the derivative of the local energy, and that, of course, has this nice zero variance property. So with a good choice of q, that term isn't a problem. So if you want to implement this, you can actually do it in pretty much the same way as forward walking. Whereas now, I have a vector associated with each walker, and at each step, I have my individual sample of the logarithmic derivative of the Green's function. But instead of just looking at a single sample for my weight, I need to do a back sum over all the previous weights. So the easy way of doing this, of course, is to have a finite vector and the sum, and then kind of do a push in, push out on the vector, and then add the newest value, subtract the oldest value, and keep a running sum going. Of course, this is trivial to implement, and you can do any number of back sum lengths that you want, but eventually you'll still run into the same problems that you do with forward walking. There is this instability, because the signal to noise ratio of the first order mixed distribution will decay versus the mixed distribution itself. Having said that, though, you can actually do nice things in practice with it. So again, here's the force in H2 that we had before, with the same trial wave function, 1s on each nucleus, and applying this method gives you the exact forces back, even though we've done nothing with the trial wave function. So, of course, in this case, there's no nodes, so that's not a problem. But forces are notorious, and they have more divergences than they know what to do with. And we have a nodal infinite variance term as well.
How is that last piece different from the Hellmann-Feynman sampling?
I'll show you what Hellmann-Feynman sampling is in a minute.
I know what it is.
No, I mean,
what the difference is.
I'll show you the difference in a minute, because there is a distinct relation between the two. Yeah. So nodal infinite variance is different to this algebraic infinite variance, which is caused by a physical location, so electrons getting close to the nucleus. In this case, the irony is this term, this derivative of the local energy that gave us our zero variance principle, actually has a 1 on psi t squared problem. So as you get close to a node, this term's going to diverge, and you've got your infinite variance back again. So one way of getting rid of that is to say, well, let's just ignore this nodal response term. The response of the nodes to the perturbation of moving a nucleus must be tiny. So what happens if we just completely ignore it, set that to 0 on the nodal surface, and see what happens? As an example of how the infinite variance manifests itself, this is one of Richard Need's group calculations where they see these very, very long-range tails appearing. So this is the frozen node approximation, and we've only applied it to a couple of things so far, so I'll just show you BH. And in this case, so this was a very simple DMC algorithm. So we used, what was it? I think it was a very small Hartree-Fock calculation with an electron-electron gestro just to get the cusps right, basically. And in this case, here we have the DMC value, the approximate zero bias correction, which just overshoots on the other side. And then this black line is, again, the fit to the DMC NGs. And you see that we get a very, very accurate agreement. So neglecting the nodal term in this case seems to be insignificant. Whether that's going to be true in general, I don't know. But we're looking to see. So this is what you asked for. Right, so if you take your first order trial wave function and neglect it entirely, then you're throwing away the chance of doing any improved variance calculation. So you wouldn't be able to do a force, for example. If you did that, then you'd only get a contribution from the branching term of the Green's function. So the del Q that you had before would go to 0. There's no contribution from drift diffusion. And this is identical to what the Hellmann-Feynman sampling expression is. which in itself is actually virtually identical to the Boronet and Casulleras forward walking expression, which in itself is almost the same as the Nightingale expression that I showed at the beginning. So they're all related in certain ways, they're just slightly different ways of doing it. So you compare this expression from Hellmann-Feynman sampling that has the bare estimator in it with what we have with our importance sampling, essentially, and we have a zero variance principle in these quantities, whereas in Hellmann-Feynman sampling you don't.
So you're saying that you use, in the zero variance or Vines branching term that you have here, that d lambda e local is the estimate that you get after you apply the zero variance correction?
Yeah, so the derivative of the local energy, so that sample is the derivative of the local energy if you assume that psi t doesn't change with your perturbation.
Okay.
Yeah, because the first term you get is a psi t on psi t. So basically, the point is with Hellmann-Feynman sampling, you can't do an estimator that would ordinarily have infinite variance.
So this is a local term, d lambda e local. So whenever you do, if you're looking at a term due to a correction some number of steps in the past, you're using a local estimate on something that you've already projected on?
Mm-hmm.
Okay. And so then the first order correction is something that looks like an operator on psi trial over psi trial,
Yep.
but you're then putting in a psi 0, psi t expectation value so that you gain some,
Essentially.
you still get some contamination from the trial wave function in that case.
No.
Okay, well we could talk about this later.
Okay.
I don't understand that.
As long as the nodes don't change, there is no contamination whatsoever. Okay, I'll go on. So all this is assumed that we just took the derivative of the Green's function to get the derivative of psi naught psi t. And of course, that assumes that this is our nice, clean expression of how we propagate our DMC. But we don't really do that. I mean, we do things like Metropolis. We do things like different forms of del psi t on psi t to get rid of divergences, like in the Umrigar-Nightingale-Runge algorithm. And that has a really large effect on the time step errors. So here's an example of the DMC expectation value of some quantity, which I've shifted to agree with the exact value, by the way. It should be up here somewhere, using a DMC algorithm with a simple Metropolis accept-reject step. So we have a very small time step error, basically. This is time step along the bottom, tau, and then the value. The problem is, because we just differentiated the Green's function, we get this huge time step error in the zero bias estimate. It'll always agree at tau equals 0, but anywhere away from that, you're going to get terrible answers. So the question then becomes, how on earth do you differentiate the Metropolis step? It's not usually written in DMC as, here's Metropolis DMC, as an algorithm, as an expression you can differentiate. It's usually written as an algorithm. So here's my attempt at writing it as an expression we can differentiate. So what we do is we take our normal propagators. I've gotten rid of the time step dependence just to keep everything manageable for now. And we just have our branching term and our drift diffusion term. And what that actually becomes with Metropolis is a branching term multiplied by your Metropolis Hastings, what's the word? Transition probability. That's the word. Okay, so what is the Metropolis Hastings transition probability? Well, it's your original drift diffusion term, which was your trial move, multiplied by the Metropolis accept-reject, but then there's also this term that allows the step to stay where it was in the first place, right? And this makes things a little tricky when you think about what it's actually telling you. So this is saying, I propose a move, I accept it with that probability, but there's this probability that I will stay where I am. And the reject probability is written as the probability of trying every single possible step and being rejected from it. But that isn't what we do. I'm proposing a move, either accept this move or reject this specific move. So just doing the normal thing that you get when you try and work with Metropolis Hastings is useless. So thankfully, you can write this in terms of what I interpret as being what to do for a single step. So basically, this expression is your normal transition proposal, and then you have two terms weighted by the accept and reject. So this is an accept probability, and then that means move this step to being your R primed, and then reject that specific step, and then keep your R primed at R. So once you've written it in this way, you can actually just go forward and differentiate it. And if you do that, then you get this horrible expression, but it's nice and easy to interpret. So the blue term is basically saying, well, this is what the derivative looks like in terms of logarithmic derivatives if I've accepted this specific step, and this is what the logarithmic derivatives look like if I've rejected this specific step. So now I have a recipe. I weight by one of them if I accept, I weight by the other if I reject. Turns out that in certain systems, and I don't know what the class of systems is where this happens because it doesn't happen all the time, you get really, really large variance if you just do that simple thing. But if you do the whole expression and just weight them by the accept and reject probabilities, then you get a much, much improved variance. Now, I know this happens all the time in DMC, but there's never usually a much gain to be done by that weighting. It's usually a very small effect, but in this case it can be quite large. So what happens when you do this? So the green, as before, is the usual DMC result for an expectation value. The red was just differentiating the normal Green's function, and now the blue is differentiating the entire Metropolis Hastings step. So you get a very, very much improved time step error. So I've done one. I've gone through this quite quickly, but there's one last thing I want to talk about, which is differential operators, which is a quick experiment because I only thought of doing this the other day. So basically, forward walking has this problem we know where even if you had the exact distribution, you would still be operating on the trial wave function. So you could never get the exact expectation value of a differential operator. There's nothing to stop you doing that with this zero variance approach. The perturbation theory doesn't say anything about having to act on anything. The term that's correcting your mixed distribution expectation value is an additive term. It's not multiplicative. So in principle, it can correct anything. So I thought about how you might go about doing this with this zero-bias DMC. And, sorry, yeah?
I just wanted to comment that you can do this in a forward walking scheme. It just requires a non-local move.
Okay.
For instance, if you look at a paper with Marcus Holzman as the lead author, we do this for the momentum distribution.
Okay.
On gas.
I wasn't aware of it.
Yeah.
Okay, right. Well, okay, it can be done in forward walking, but you can also do it in zero-bias DMC. So the way you do it in this case is you go back to your original imaginary time diffusion equation and you perturb it before doing the importance sampling transformation. That's key to doing it. And then you have, so in this case I'm doing the kinetic energy. So I'm taking my diffusion constant and I'm just transforming it to d into 1 plus lambda, where the diffusion constant as usual is a half, but it's just easier to keep track of if you write it explicitly. When you do that and then do the importance sampling transformation, you get a lambda-dependent Green's function. So in principle, you could do this for any operator, but you would have to find your lambda-dependent Green's function before you could do anything else, and that might be the hard bit, I suppose. So this is fairly straightforward. We can go through and differentiate this, and we do so. And the first term is a constant, and we don't have to worry about it. Then we get contributions from, well, this is only the contribution from the drift diffusion. Of course, there's a contribution from the branching as well, but this is the interesting one. We get the usual terms, but then we also get something which we might be able to do something with importance sampling. So I haven't been able to do that yet. I've got a potential estimator that will work for kinetic energies, but I haven't implemented it yet. What's more troubling about this is, are there problems near nodes? So for example, here I've got a v dot v, and I've got a v dot v up here. So that looks like it's going to be a quadratic divergence near a node. Potentially, a good value of del Q might be able to do something here, but it's too early to say. So here's what happens if you don't have a Q. If you just use the branching contribution, then you get the naive forward walking result, just with the local moves. But if you include the drift diffusion terms, then you get the exact result, but with this massive error bar compared to the branching terms. So I guess the next thing to do is find out if this estimator for kinetic energy will work. So that's pretty much it. So thank you for listening.
Questions, comments? Paper that you mentioned, for example, I think it was the branching algorithm that was the particular.
It was done in reptation, but conceptually it's identical.
So kind of difficult to see how to do this with branching actually.
No, so you can imagine doing a DMC calculation, all right, and and then create an ensemble of walkers, in which then you take a single, just with momentum distribution, take a single electron and throw it, then continue the random walk, and look at that point at the descendants from that particular off-diagonal move, and that will give you the correction to the trial wave function ratio.
For one configuration, which is very...
I'm not saying that it is computationally efficient. Reptation makes it a lot nicer, but you have nice parallelization algorithms for diffusion.
So
Do this.
does that apply to any differential operator?
Any non-local operator.
Any non-local operator? Okay.
Yeah. I mean, and that's just in the sidewalks type of algorithm. You can do this on the fly. I mean, you can be more clever about it.
Okay.
Isn't it just easier to take the total energy and subtract the potential
Of course it
energy
is.
in general?
Of course.
My sense is that people don't look at kinetic energy precisely because they end up doing it.
Yeah, yeah. No, I mean, this was a conceptual thing. The idea was, could you do any operator whatsoever? And yes, you can. You just need to find a lambda-dependent Green's function to do it. So it was just me playing around, basically. But yes, you would just separate the, especially because you can get zero variance operators, estimators for the potential energies. So you can make those absolutely tiny. Yeah.
I have a comment on the fact of neglecting the nodal dependence. I have no idea what is the effect on the first derivative. You showed an example where the effect was very small, but I know that the effect is huge for second derivative.
Is it? Okay.
It can be 10–20%.
Right. Okay. Not the way to go then. Not the way to go then.
Yeah, I mean, in my experience, forward walking and the Hellmann-Feynman sampling both produce statistically
Yeah, they're identical.
good results, though. I mean, it's
Yeah.
not. You have to be careful, though, because sometimes you think you've plateaued and you haven't, and you have to go further, and there's like a second peak, depending on how bad your trial wave function is. But in general, the zero variance contribution that you get when you just apply, you take the derivative of your total expectation value. It gives a non-zero contribution at the DMC level. I mean, you can show this.
Really?
The zero variance part.
Oh, the zero variance part, yes,
Yes,
but you
that's
then
it.
have to correct it with the zero bias part.
Yeah, but you can include that entire piece. Like originally, I think that the first time that expression was written down was in the Nasseroff and Caffarel paper before the Hellmann-Feynman paper. I think Coronat and Casouris came out. And anyway, we can wait until the afternoon, but in that paper there is an explicit term that is the zero variance piece as well as the zero bias piece. Yeah.
Yeah, I mean, it depends how you think about it, because you can take the entire expression and like you can throw away terms. So like I threw away the d lambda psi naught, and then you just get back the mixed DMC estimate, but with a zero variance. It's if you include the approximate zero bias that you get something that's not the mixed DMC and not the exact, and which hopefully is perturbatively somewhere in between them.
Right, in the Hellmann-Feynman sampling paper that was written, I think that they threw away the entire zero variance piece and just kept the correlation function part, right?
There's no zero variance in the Hellmann-Feynman sampling.
That's right.
Yeah. They didn't even start with it. They just said, let's differentiate the algorithm rather than differentiate the energy. So all they're doing is differentiating the weights, the branching weights, basically.
I understand.
Yeah.
So Sabrina was talking yesterday about replacing the branching green function with the branching with the green function with psi trial, and
Yeah.
so could you see combining that with your time step, improved time step algorithm? Do you think that will work?
No, that's what that is.
Oh,
That's
I guess
it's directly equivalent to choosing d lambda psi naught to be equal to d lambda psi t, or the logarithmic derivative. It's exactly the same. Because if you differentiate the green, if you're assuming the Green's function is psi t squared in some limit, then differentiate it and get 2 d lambda psi t on psi t. So.
Okay.
Okay.
Anyone else? If not, we combine at 3:30 and thank you, Manolo.